this video, I'm going to illustrate further notes on stability. Once again, the same definitions. We need to look at the characteristic equation of our difference equation. And actually, in this video, I'm going to use a slightly different initial value problem. It's a non-linear one, just because it helps with looking at oscillations. So, if n is equal to 100, step size is 1 over 100. We're interested in solutions between 0 to 0 to 10, and so we have our method. Our first method is a stable method. Very straightforward. Wi plus 1 is equal to Wi plus h over 2, 3 times f. So this is just the two-step Adams-Bashford. Now, and this has the root condition of lambda is equal to 0 and lambda is equal to 1, so it's strongly stable. The second method is weakly stable. Wi plus 1 is equal to 1.0 Wi minus 2. So it's I minus 2 here is the issue. This does not satisfy the root condition. This does satisfy the root condition because lambda is equal to plus or minus 1 and plus or minus square root minus 1. So therefore, it's more than one root of lambda, so it is weakly stable. And lastly, the unstable method. I'm using the exact same method as up here, except I'm adding 1.001 to the top. It's an arbitrary number, so our characteristic equation of lambda squared is equal to 1.01 lambda. So it's a very, very small change. Now, our methods, we have to style up our initial conditions, and then we just input our methods. They're all more or less the same. It all works its way through. But what we see here is the stable solution is monotonically decreasing. The weakly stable, like in the previous example, has this oscillation in it that's not natural. But the unstable, or the not stable condition, it just ticks off to infinity in the opposite direction. Everything else is monotonically decreasing, it is monotonically increasing because of this 1.01. It means it's getting larger in every single iteration, larger than it should. And even though this is 1% bigger than the other, it completely destroys the solution.